Okay, bonjour à tous, bonjour à toutes. Voilà, good morning everyone. Sorry. Welcome to this PhD defense. So first of all, my name is Mainia. I am professor at INSA Defense, and today I have the pleasure and the honor to chair this this PhD defense committee. Before giving the floor to the candidate, before giving the floor to Timotée, I would like first to introduce the members of the examination committee. First, we have two reviewers, Professor Nicolas Gac from Université Paris-Saclay and Professor Heidi Tabia from University Ivry-Val-de-Saône and Saclay. And then Professor, as I said before, Professor Nicolas and Professor Heidi served as reviewers of the thesis. Next, we have Professor Jovita Lukasik from the University of Siegen in Germany. Good,
yes,
good pronounce it, good? Okay, okay. So Jovita is also a member of the examination committee. The PhD research was conducted under the supervision of Professor Abdeljalil Aysal Bey and Mathieu Leonardin from EMT Brest. So the defense will proceed as follows. First, Timotée, the candidate, will first give a presentation of the thesis in about 45 minutes, and then we will have Q&A session. So in this Q&A session, we will have discussion, we will have question and answers, and then we will deliberate for the PhD. So you have the floor, Timotée.
Thank you very much, Mr. President, for the introduction. Today, we'll be presenting the works conducted during my thesis titled Methodology of Efficient Neural Architecture Search, Metric-Driven Frameworks for Supponent Splitting and Zero-Cost Evaluation. And as you said, this was conducted under the supervision of Abdeljalil Aysal Bey and Mathieu Leonard. So first, for some context about the subject at hand. When it comes to deep neural networks, there are several types of parameters that you may encounter during the process of making the neural network pipeline. There are, of course, the trainable parameters, which are tuned during the training of the neural network, and also the hyperparameters, which serve as the base parameters of the algorithm itself. And for these hyperparameters, there are two subtypes. The hyperparameters for the training, which could be something like the batch size or the scheduler itself or the number of epochs. And there's also the architecture, which is the mathematical definition of the neural network, and which is the subject of today's defense. It turns out that there is a field dedicated to tuning these hyperparameters, which is called hyperparameter optimization. And the field that we are looking at ourselves is a subfield of HPO called neural architecture search, which is dedicated to the tuning of the architectural parameters themselves. So traditionally, these hyperparameters were tuned by human experts, but there are several reasons why one may want to use HPO and NAS instead. And these reasons include gaining some time, having a more consistent tuning, also taking advantage of the multi-objective capabilities of both the HPO and NAS frameworks, and finally, being more adaptable to some tasks that are not commonly seen in the datasets. So let's start with the mathematical definition of neural architecture search. So this is an optimization problem with 2 layers. The first one being the inner stage of the optimization, which is simply the definition of the training of a neural network with respect to some training loss. And as for the outer stage, it is the NAS objective itself, where O is an objective function which remains to be defined during the definition of the problem, which could be validation accuracy in the most standard case, but there are other alternatives such as memory imprint or latency, or even a mix of several objectives. In practice, how is neural architecture search done within the methods? Generally, the methods follow a 2-step pipeline where each step of the pipeline corresponds to one of the layers of the optimization problem. We have, on one hand, the architecture sampling, where an architecture is drawn from a search space, and the evaluation, where where the architecture is evaluated with respect to a performance. And typically, this performance is, of course, the validation accuracy, which is the objective of the search or some other objective. And it is treated as some kind of performance level to train the sampler. And this leads us to the main bottleneck of neural architecture search, that being the high time and computational costs of evaluating the architectures. And this is because in a typical NAS pipeline, we would want to train fully the architectures from scratch, and we also need to do this many times in order to train the sampler properly. And in response to this bottleneck, a sprawling literature has emerged with different families of NAS methods, ranging from, of course, the standard NAS methods with full architecture training from scratch, and then other families that perform performance approximation based either on some supernet methods or some zero-cost proxy methods. And in this thesis, we will be tackling two of the subfamilies, those being few-shot neural architecture search and zero-shot neural architecture search. So in few-shot neural architecture search, our goal will be to divide the space in such a way to make the search easier, while zero-shot neural architecture search will take advantage of the inner properties of the models using some metrics called zero-cost proxies. So first, we will be giving a thorough check of the technical background surrounding this thesis, and in order to best comprehend our contributions, then we'll move on to our first contribution, which is the generalization of the few-shot NAS framework using metrics. And finally, the third part will focus on the zero-cost proxies and their benchmarking. So in this first part, we'll be focusing on the technical background of neural architecture search. So first of all, there are several components to a full NAS pipeline, which are kind of multi-layered. As I described before, there's the NAS method itself with the sampling evaluation paradigm. Then there's the search space, which needs to be defined prior to the NAS method in order to define which architectures can be found in the first place. And the overarching structure is the application, which is what we are trying to use NAS for in the first place. So I will be tackling these components in order from least to most relevant for my thesis. So first of all, the applications. At the beginning of neural architecture search, the goal was definitely to discover state-of-the-art architectures based on neural architecture search. Nowadays, this is less often the case, and this is because for state-of-the-art deep learning, most of the time the architectures that are used are transformer-based. And in the case of transformers, and especially transformer for large language models, we know that there exist scaling laws that are both more effective and more efficient to find the optimal architectures. So the goal does tend to be not so much discovering state-of-the-art architectures anymore. Some actual NAS applications that could be seen in the real world nowadays are hardware-aware applications. And this is because neural architecture search can be exploited, and its multi-objective capabilities can be exploited to search, for instance, Pareto fronts in very hardware constrained contexts. So now let's define the concept of a search space. So what is a search space? It is simply the extent or the collection of all discoverable architectures that exist within our problem. And this collection is generally defined in a mathematical manner such that many architectures can be defined at the same time. And this leads to this scale where the search space may go from being very constrained, in this case, for instance, for some benchmark search spaces, such as NAS-bench-to-1, which we'll be talking about more. And on the other hand, we have some some search spaces with very little constraints. And a good example of that would be the very recent Einspace search space, which opts to define the architectures from basic grammar, which makes it very expressive and free. These search spaces have tended to be grouped in several categories, and the bigger archetypes of search spaces would be the complete or macro search spaces, which actually have existed for quite a long time. The very first search spaces used in neural architecture search were of this type, where each operation corresponds to one choice that is possible in the space. And this the more recent spaces such as Einspace continue this legacy of having a lot of different choices in the model. The second type, which is most important for the benchmarks, would be the cell-based search space archetype, where the deep neural network is defined as being a stack of cells, and each cell having a limited number of operational choices inside it, which makes these search spaces very lightweight and very easy to explore and benchmark over. And the final type that we'll be giving an overview of is the block-based search spaces, where the structure is a stack, just as the cell-based search spaces, but each block can be defined separately based on some predefined deep learning blocks, such as a ResNet or transformer. And compared to cell-based, this is very underexplored. There's, to my knowledge, only one benchmark, which is blocks. And although this is much more suited to the current practice of deep learning in the literature, as for instance, transformer models operate in this block-like fashion. So I'll be now describing some common benchmark search spaces that will be useful for the rest of this presentation. The first one would be NAS-bench-to-1, which is the most popular search space overall in the literature and the one most widely used as a benchmark. So NAS-bench-to-1 is defined as a stack of cells as I explained, in the cell-based fashion, where each cell is quite reduced in size, and it is formalized as a directed acyclic graph. So this is something that is quite important to understand, to understand cell-based search spaces and how we'll work with them. So in the direct acyclic graph formalism, the nodes of the graph are features, while the edges are operations that we can choose based on the choices provided in the search space. And so, for instance, a cell of the search space would look like this, where each color of the edges corresponds to a different operation. And then the cells are stacked on top of each other with some reductions in between to form a full network. And the cell is always the same across the network, so it's cloned. Another search space that is quite common in this fashion is the Dart search space, which was introduced in the Darts paper. And the main difference with the NAS-bench-to-1 search space is that there are now two cells to discover, the regular cell and the reduction cell, which is located at each moment of downsampling in the network. And compared to NAS-bench-to-1, which only has 6 edges and 5 operations, this one has more edges and operations. So it's a lot bigger, and this has made it a good benchmark space for state-of-the-art NAS, as it's not easy to discover the optimal architecture on this search space. So the fact that there exists some benchmark search spaces that are very small, such as NASBench 201, makes it possible to tabulate them. And what do we mean by having some tabulated benchmark? This means that for this specific search space, so in this case, I represented NASBench 201, on several dataset tasks, all of the architectures of this search space have been trained exhaustively. And for NASBench 201, this is the case on the SAFA 10, SAFA 100, and ImageNet 16 tasks. And once all of the architectures have been trained, this creates a lookup table, which makes benchmarking very easy, which means that we have the performance of every architecture in this search space. And a number of other tabulated benchmark search spaces exist that also have other use cases. And an important one would be the Trans NASBench 101 search space, which focuses on other diverse tasks in the image paradigm, such as semantic segmentation or object detection, still in a search space that is quite similarly designed to NASBench 201. So now that we have the search space, the next topic at hand would be architecture sampling. So I said earlier that evaluation was the main bottleneck of NAS, and this is the case because sampling was actually solved quite a long time ago in the literature. And generally, it is accepted that there are three main categories of sampling algorithms, of sampling ideas, those being Bayesian optimization, where a model of the search space is kept such that, where architectures can be sampled from. Graph neural networks, which is the idea that some graph neural networks can generate other architectures and which can then be evaluated. And the final one is genetic algorithms. So I will be describing genetic algorithms more in depth since we did use them quite a lot during this thesis. So in the genetic setup, in the case of neural architecture search, as in every genetic algorithm setup, we are keeping a population of items, and the items in this case are the architectures. And then based on some fitness rule, we want to either make these items reproduce following two operations, which are mutation and crossover, or we want to discard them. And specifically in the NAS context, most of the time we are using elitist evolution, which means that the architectures that are discarded are the worst based on the fitness. And this is as opposed to aging evolution, where the discarded architectures would be the oldest. And another quite important aspect of genetic setups for neural architecture search is this tournament selection idea. This is to solve some stochastic issues of the genetic setups. And the idea is that at each evolutionary step, instead of using the whole population, we'll be using only a subset of the population to evaluate. So this leads us back to this core bottleneck of NAS that I described, which is the evaluation. As I said, in standard NAS, the idea that we need to sample architectures and then train them from scratch to obtain this performance label means that there are very high time and computation costs incurred. And this has actually led to the true main question of neural architecture search: how to best approximate the performance of sampled architectures. And it is this question that is that tends to be answered by the families of neural architecture search methods, which can be grouped as with some kind of family tree. With on the far left, we have the standard NAS methods with full architecture training, which means that we do not try to answer this question, this problem that we just posed. And on the other side are the performance approximation methods, where we do actually try to approximate the performance based either on supernet methods or zero-cost proxies. So in timely fashion, I will be explaining both of these ideas. First, since it will be useful for all of our contributions, I will define the idea of the zero-cost proxy. So what is a zero-cost proxy? It is the idea that architecture evaluation can be bypassed by using some theoretical metric that describes innate properties of the model at initialization, which means that we never actually train the model. And in the pipeline, this metric would directly replace the performance label that would otherwise be the architecture training. So what kinds of metrics are we talking about here? Some examples include trying to quantify the flow of the gradients inside the model. So those would be metrics such as the norm of the gradients, or some other metrics based on the pruning literature, such as scene flow. Some other ideas include using the NTK theory, which focuses on the dynamics of the training, and also evaluating the expressivity, which is the extent of possible functions that our model can approximate. And this is actually quite easily approximated in ReLU networks with some geometrical considerations. One other thing that is quite important to explain when it comes to zero-cost proxies is how we are going to benchmark them. So if you look at zero-cost proxy papers, you will come across this kind of tables. On the x-axis, what you have are the tasks that we're using, and these tasks are defined with a search space task pair. For instance, here on the left, we have NASBench21 on the Cypher10 dataset, and then later on, you'll find trans NASBench101 on the segmentation task. And on the y-axis are the metrics that we seek to benchmark. At the intersection will be a value that is some kind of correlation between the rankings made by the metric and the true rankings of the architectures. And generally, this correlation will be the Spearman rank correlation, which seeks to evaluate how linearly correlated the two rankings are. All right, so now with all of the theoretical backgrounds explained, we can move on to the core contributions of this thesis. So the first one will be our contribution to generalize the few-shot neural architecture search framework using the zero-cost proxies. So in order to understand what setting we are placing ourselves in, we must first understand the concept of SuperNet-based neural architecture search. So the basic idea of the SuperNet is that instead of training each architecture separately, we are going to group the entire search space inside a single model. And then because this model represents the entire search space, we only need to train a single time to obtain the performance of all other models in the space. So if we go back, for instance, to the NASBench21 example, a DAG representation of the SuperNet would be the following, where we have all of the possible architectures that are grouped on each edge, and how they actually form a SuperNet in practice is by either summing them or concatenating them when going into the features. And then simply by deactivating some of the operations on each edge after the training, we end back up with the base architectures from the NASBench21 search space, which are defined with a single operation on each edge. So in terms of the methods that are generally seen for SuperNet-based NAS, there are two main families, differentiable NAS and one-shot NAS, although one may sometimes see one-shot NAS used as a term to describe the whole SuperNet framework. In the case of one-shot neural architecture search, the pipeline is as follows. So we sample architectures, and then with the SuperNet that has been trained beforehand, we copy the weights of the SuperNet onto the architectures and say that these weights represent the trained architecture. And on the other hand, in the differentiable setup, the SuperNet is trained and informs the sampling at the same time by embedding some differentiable parameters inside the algorithm loop. So in both cases, SuperNet methods tend to suffer from some reliability issues, which includes the very well-known and very well-studied issue of coadaptation. So what does coadaptation say? It is the idea that on a SuperNet, the operations that are on the same edge would not be able to converge properly when trained together, although they could converge adequately when trained in isolation in the standalone architectures. And the idea would be that the gradients, for instance, would point in opposite directions, which would lead to a training that is unsatisfactory for all operations. And this is one of the main issues that the entire SuperNet sub-literature tries to tackle. So in this context, we can see that we already have different ways to approach NAS in terms of how many architectures we are going to train. If we do no NAS at all and just do an exhaustive search, then we train everything. The standard NAS pipeline would be to train many times in order to fit our sampling algorithms. Then if we train only once, that is SuperNet-based NAS or one-shot neural architecture search. And in between all of this must be some kind of few-shot neural architecture search where we train a few times. And so this idea was first explored in a paper by Xiao et al. In 2021. And how they did it is that they started from the SuperNet DAG representation, and on each edge they splitted the SuperNet based on each operation on a single selected edge, which results in however many sub-SuperNets as the number of operations that were on that edge. And so, for instance, here in the NASBench 2.1 context, we start from the SuperNet with 5 operations on each edge. And on the first edge, we can see that we have split it into one sub-SuperNet, each having a single of the operations possible. Then later on, another paper by Hu et al. Said that probably this coadaptation idea, this coadaptation problem might actually not need to exhaustively split between the operations. And actually some operations might benefit from being trained together, just not all together. So what they seek to do was to learn what splits need to be made in order to optimize the splitting. And they did so by matching operations based on the gradient matching metric, which is basically the cosine similarity of the gradients of the operations when they're trained in isolation. And the advantage of this technique is that we can go further down the splitting tree since we are splitting into less groups. So, for instance, after having split the first edge, we can move on to a second edge and also make other groups that may be optimal. So this line of work leads us to a new problem that we call the generalized splitting problem, which states how do we split the base SuperNet in order to maximize the performance when we end up searching from the sub-SuperNets. And for this, we have to understand that on the sub-SuperNets, we are going to search using some SuperNet-based methods such as a one-shot or a differentiable algorithm. So to answer the question of this problem, there are several components. The first one, of course, is how are we going to split? And that is what we called the splitting policy. And for instance, in this gradient matching paper, the splitting policy was to always split into 2 groups, which means that we will always end up with a number of sub-SuperNets equal to a power of 2. And this is some kind of splitting policy. And on the other hand, we have the problem of how are we going to group the operations. And so, of course, gradient matching introduced the gradient matching metric to group these metrics together. But we generalized this idea such that any metric can be used to group the operations. Something that we called the metric-driven framework. And how do we do so? We isolate the operations on the edge that we split. Then we evaluate them using the metric that was chosen, which is in our case would be a zero-case proxy, which is because they already exist in the literature, so it's intuitive to use these proxies as well. And then based on this, we are going to obtain some similarity matrix of the metric scores for this specific edge, which will allow us to group the operations together. So of course, this framework we would want to benchmark it, but before even benchmarking with some numbers, we can look at the innate properties of the split. And in order to do so, we can use a mathematical tool that we introduced called the split distance. And so basically, what the split distance does is we just count how many operations we need to move to go from one possible split to another. And based on this metric, we obtained already some preliminary insights. What we plotted was the split distance for various different metrics, and we found that they tend to operate and interact with the splitting in different ways. And the first one being that some of the metrics had very low split distance, which means that they tend to make often the same splits, while others were more exploratory, having higher split distance, which means they were more akin to make various splits. Now going into the benchmark. So for this benchmark, what we did was we chose 9 different operations, as well as the NASBench2-1 subspace, and we conducted some 4 different downstream one-shot NAS algorithms in order to benchmark the final performance, and which we also did on the 3 tasks of NASBench201. So what we found was that, first of all, when we split the supernet, we always have better performance than when we don't split and apply the supernet algorithm natively. And this actually hints at the idea that splitting is always beneficial no matter the metric. But when we look at the results by metric, then we find that there's no clear winner among the metrics. Depending on the task, depending on the algorithm, we may find that it is a different metric that is best suited for the splitting task. So overall, this may indicate that the performance gain is not so much the work of the metrics and more so of just reducing the size of the search space. And this intuition can be further explored by plotting the distributions of the splits. So on this slide, what are we looking at? So each of these plots represents one of the subsupernets that we obtained after the splitting. We split it into 8 subsupernets, so there are 8 plots. We have to remind that we are working on a tabulated benchmark, which means that we know in advance the true performance of every architecture. And this is what allows us to create this distribution plots with the validation accuracy on the x-axis and the bins of architecture on the y-axis. The grayscale distribution is the full distribution of the search space, the NASBench2-1 search space. And the colored distributions are what we obtain inside our subsupernet splits. And so first of all, we can see that they tend to be unevenly distributed, with some subsupernets having a lot of the distribution, while others not so much. But the most interesting part is that if we zoom on the top 1% of the distribution, which is at the far right of the distribution tail, we find that the architectures tend to be distributed, the top architectures tend to be distributed among many different subsupernets. And so this means that if we choose one subsupernet, then it is unlikely that we will find the best architecture, because all the best architectures are grouped in very different subsupernets. So to conclude this part about future dual architecture search, we introduced a generalization of the base NAS framework that allows us to utilize different metrics that are mostly arbitrary, but we used the zero-cost proxies in our case. We demonstrated that few-shot NAS outperforms a regular one-shot NAS in most cases, but that there is no best metric for the splitting. And we also highlighted that few-shot NAS comes with its own issues that are specific to this line of work. Some perspectives about this work. As I said, maybe most of the performance gain is actually attributable to the fact to the search space shrinking aspect of few-shot NAS. And it should be noted that our results could be improved based on the fact that the benchmark search spaces that we are using are very constrained and very shallow. So this is something to keep in mind as when interpreting all of these results. And these were the contributions that were that we made during that were part of this line of work. All right, so in this first part, we only used the zero-cost proxies as a tool for the splitting of the sub-supernets. In this next part, we'll be actually focusing more specifically on the zero-cost proxies and the framework surrounding them. So first, let us recall the pipeline of zero-cost proxies. We have the evaluation, and we want to replace it with some estimation based on some metric that is theoretically inspired. So this is the same benchmark that I showed earlier, and this one is one of the first things that we did when working with zero-cost proxies. We benchmarked all of the existing proxies and added the proxies that were state-of-the-art at that time that had not yet been fully benchmarked. And as we can see, it depends on the task, but sometimes zero-cost proxies can obtain respectable results in terms of Spearman correlation. However, when we restrict the space on the top 1% of architectures, and once again, this is possible because these tasks are tabulated, which means that we know where the top 1%, the true 1% lies. When we restrict the benchmark to only this portion of the space, we find that there is a collapse of the performance of these proxies. This hints at the fact that while the zero-cost proxies are able to differentiate between bad architectures and good architectures, when we reach only good architectures, they are unable to rank properly in the right order the architectures. So there are this is an issue that we dubbed the top rank gap. And there are several ideas to address this problem. The first one would be to tackle the benchmark itself. So Spearman rank correlation, it's a global indicator. It does not really look at what part of the search space we are located in. And ideally, because the main objective of NAS is to find the best architecture, not just some best architecture. Ideally, we would want the ranking of the architectures to matter in the benchmark metric. And this is where Spearman does not fall short. So we introduced another metric which actually already exists, but we propose it as a possible solution to this problem, which is called rank biased overlap. So what does rank biased overlap do? There's two components. On this side, we have the agreement between the two rankings. So the ranking of the metric and the true ranking of the architectures. And on the other side, we have an exponential decay. And this ensures that as we go down the ranks of the architectures, the items will become less and less important, which means that the metric focuses specifically on the best architectures in the space. So, of course, this means we introduce the hyperparameter P, which is the exponential decay, but we can tune it and, for instance, say that the top 1% of architectures should contribute to 50% of the RVO, which should make it possible to see some differences compared to Spearman rank correlation. And in the end, by rerunning the benchmark, these are the numbers we observed. So these are not directly comparable with spin correlation because with the sum here, the values do not directly go from -1 to 1. But by analyzing the results, basically the takeaway was that it cannot replace outright spin correlation, but it can be a companion metric to explain some other effects that were not caught. And so this problem of the benchmark metric remains an open topic. So the second aspect with which we wanted to tackle this top rank gap problem was through the methodological lens. And for this, we introduced our Paradis method. So this is a genetic framework where, as in other genetic frameworks, we keep a population of items, which are architectures. Then we have some fitness to explore the space by replacing iteratively the architectures in the population by imitation crossover. And our fitness here would be a zero-cost proxy, because we believe zero-cost proxies are suitable to explore the space, as that's what they were designed for. However, for the discarding architectures part, we opted to use instead our own custom-made discriminator, which removes architectures based on some considerations of the parameter count. And this is based on the observation that in many anterior works, parameter count was actually such a strong proxy that it's sometimes not very justifiable to use actual theoretical insight proxy compared to simply counting the number of parameters. So by embedding the parameter count directly inside our algorithm, we believe that the bias on parameter count would be removed. And some things that are quite important to observe about our framework. First of all, we designed the discriminator in such a way that it does not use any insights from the knowledge of the space. So actually, this discriminator idea was used before in other papers, but they always exploited some knowledge of the space, such as, for instance, knowing the average parameter count or the standard deviation of the parameter count. And we only used the population, so we remain agnostic in this regard. And another consideration is that although our method is not data agnostic in general, when we're using specific zero-cost proxies, we can become data agnostic. And that's the case, for instance, with the SynFlow metric. So why is it important to be space agnostic and data agnostic? First of all, we need to be able to generalize to various spaces. So that's why we remain space agnostic. And of course, this would be very important for very expressive subspaces such as einspace, where the statistics of the space are not easily found. And we also, in the same vein, we may want to be data agnostic in order to generalize better to diverse tasks. So here were the experiments that we conducted on our framework. On these plots, what we did was evaluate our metric in the DASBench 201 space. So the plots are quite similar to the benchmark, with the tasks on the x-axis and the metrics on the y-axis. However, what we have at the intersection is the rank of the top found architecture in the space. And so what we see is that when we don't use our discriminator, so we only use the zero-cost proxies both for exploration and discrimination, then we have very low ranks, which means that some metrics fail to obtain to reach the top of the space. And this is significantly reduced when we use the discriminator, which highlights this reduction of the top rank gap that we found. And in the second experiment, we benchmarked ourselves in the darts search space. And in this benchmark, we found that although we do not reach state of the art, we are nearing state of the art of zero-cost proxy methods, while also being the only method that can remain space agnostic and data agnostic. So to conclude with this part about zero-cost proxies, we identified the top frame gap, which is a glaring weakness of the zero-cost literature. Then we tackled it in two ways. The first one being the benchmarking lens, and stating that better benchmarking objectives could lead to the construction down the line of zero-cost practices that are more robust to these kinds of issues. And we also introduced our own method Paradis, which is a simple space and data agnostic pipeline. And this Paradis methods highlights the fact that methodological considerations are just as important as the design of the proxies themselves. And these were the contributions that we made that are related to this line of work. So some perspectives about our work. First, a general recap of what we said during this presentation. First, we describe the technical background that is important to understand our contributions, including the applications of NAS, the search space, and the sampling methods, and also we describe the many families. Then we moved on to our few-shot NAS contribution, where we generalized the few-shot NAS framework in a metric-driven fashion. And finally, we looked at zero-cost proxies and the challenges they face. So some larger issues of the field, something that we may have noticed across this presentation is this issue of the benchmark subspaces. I believe this is one of the biggest issues currently that prevents the NAS literature from really going into the mainstream. All of the tabulated benchmark spaces that exist are cell-based, and they're also quite outdated. For instance, NAS Bench 1 is now dates back to 2020. So this is quite far from the transformer-based architectures, for instance, that we have. And this cell-based approach has never been used anywhere else in the mainstream deep learning literature. So novel NAS methods tend to have very limited adoptability at large because of this quite limited benchmarking. And some trends in neural architecture search that I am personally excited about. As I said in the first part, the main applicative field of NAS remains the hardware over NAS. NAS has seen some very promising results when it comes to exploring Pareto fronts with multiple objectives. So for instance, there was this paper by Javahiri et al., which managed to explore the whole subspace of transformers with a Pareto front consisting of latency, memory, and performance, using only parameter counts and some on-device measurements. And the other big trend recently in neural architecture search has been to go back to the roots. And by that, we mean to go back to some very expressive subspaces and try to derive direct architectural interpretation and some novel architectural ideas from these subspaces. And a very good example here would be, of course, the einspace subspace, which is based on some very unconstrained grammatical foundations and is able to contain diverse types of architectures, such as some ResNets, some VITs, and everything in between. And finally, these are all the contributions that were made during this thesis. This also includes some other contribution that we did not present here, but that is under review nonetheless. And with that, I thank you for your attention, and I wait your questions.
Okay, thank you very much. Thank you for the presentation. Now let's move to the questions. I propose to start questions from Professor Editavia, Professor at University Paris-Saclay. Do you hear me?
Yes, thank you very much. First of all, I would like to thank Timotée. The presentation was clearly good. I mean, as a complement of the manuscript that I already read. And yes, congratulations for this work. Actually, it's like spanning a lot of things, including the NAS. There is also things related to applications EEG that we didn't see here, and many other things, results. And yes, I think that you did a choice to select a few topics, so that's good. Of course, I have a lot of questions. Let's start with this suboptimal partitioning of the sub networks in a few-shot learning. The paradigm of few-shot NAS. You said that you have this super network and you would like to divide it into sub-networks. And the partitioning that I can see here could be like structurally unbalanced. Do you understand what I mean? Unbalanced in the fact that you have a supernet, you have sub-supernets, and of course you keep going down in the hierarchy. And I'm thinking that groups that you will explore probably will be unbalanced with respect to others. So there are, like, let's say group A, which is with a high probability that you will find a good architecture there with respect to another one in another path. And if your budget of computing is like equally distributed, probably you are wasting time to explore one path with respect and avoid the other, you know?
Yes, so that is very true.
Yes.
Do you want to finish, maybe?
Yeah, go ahead.
So that is very true. Actually, in the few-shot NAS papers, what they did generally is try to save some cost, some time, was to try and select the best sub-supernet at the end. And so it turns out that actually the way they did it was by using the validation accuracy of the sub-supernets themselves. So for instance, we have the sub-supernets, and then we just look at the accuracy of each sub-supernet independently, and we say, okay, so probably the sub-supernet that has the best accuracy would be the one that has the most good architectures inside. And so we conducted actually an ablation on this in our own paper. And what we found was that this validation accuracy was definitely not a good criterion. So when you try to select a sub-supernet based on the validation accuracy, generally what you have is that you don't select the sub-supernet that has the best architectures inside. And most of all, if you try to have some more complicated algorithms, such as here it was successive halving that was used, then you actually discard the best sub-supernet early. And so there's this whole sub-problem of few-shot neural architecture, which is trying also to prune down the sub-supernets and find the best one. And this, this problem is still very much ongoing in this line of work.
Yeah, okay. So if I understand, I mean, the exploration itself, it's kind of heuristic exploration. It remains heuristic. I mean,
yes, okay. It's some kind of subspace partitioning iteratively.
So I guess that it may miss a strong region of the search space, right?
Yes, it definitely does. Actually, some subsequent work tried to relax further the optimization problem by also taking into account the relationships between the edges, since we always split on a specific edge, but actually the edges have interactions between each other. So there's also another topic for this line of work.
Okay, good. Yeah, I have also questions related to the proxies or the proxy metrics that you are using here in this case.
Yep.
And yeah, I think like many NAS works using fast evaluation metrics, the proxy itself, it could be like zero cost, as you mentioned, or early training signals. These are I think it's weak prediction that doesn't fully reflect the performance, right?
Yeah, it definitely is.
The correlation may vary across data set also, and the search space may also give different. So, for instance, if I can see here scene flow or feature or whatever, maybe like for one data set, one branch, and not for the other. Right.
Yes, that is definitely. But that's what we see in the benchmarks. Some metrics perform better on some tasks, on some search spaces, not so well on others.
So many of them doesn't capture, let's say, the performance. It just capture, let's say, a point of probably partial property, partial criteria of the performance, but not the performance. So the probably more flexible metric framework does not really solve the reliability problems of the proxies. What do you think about that?
Yeah, I think when it comes to this, we kind of have to accept that these metrics are low fidelity approximations in the first place, and everything else we are doing is to kind of try to add some band-aids to fix this literature. But we know that the main goal is to have fast approximation, and that can be useful in some contexts. For instance, we are building a Pareto front. We want a lot of different architectures. So of course, this is when this is useful to have a low fidelity approximation. But of course, for the problem of finding the one best architecture, then it is not ideal.
Okay, good. So yeah, this is really very interesting. I mean, also if you be back to the figure, please, that show the subnet and the super network. I can see that the few shot NAS, it probably reduces the weight sharing bias, but it does not eliminate weight sharing, right? It's still
it's a trade-off.
So the performance estimates can remain biased approximations, right?
Yes. So yeah, it's, as I said, it's something in between train the supernet based and training many times. So it's in terms also of how good the approximation will be, it should be in between. That's the expectation, at least.
Mm-hmm. What about the methodological complexity of the framework itself? I mean, is it like adding flexibility? Is it also adding more complexity?
So I think compared to the training of the networks, the splitting itself is of negligible cost.
Okay.
And yeah.
The tuning and the deployment in practice, what it could be like easy also to have a flexible framework that guarantee the performance. Yeah, go ahead. Sorry.
So I think for an end-to-end pipeline, where basically all of the splitting algorithms and stuff are just bundled inside, then probably it would be quite easy to deploy. And yeah, generally NAS solutions have tended in recent years to be more packaged inside these kinds of frameworks. So I guess that could be implemented inside such a thing. But yeah, the method itself is a lot more advanced than some other SuperNet-based ideas.
Okay, so yeah, following this, I mean, you did applications. I mean, you have the real world application on the thing, right? because I mean the evaluation strategy and the evaluation itself has been done on this bench, which are controlled NAS bench, right? But I mean, what about the probably more realistic data with more, let's say, dimensionality? What about the scalability, the things like related to that things?
So you're touching on one of the biggest pain points, I think, of the literature, which is that actually all these methods, including not just pure NAS, but also everything SuperNet based, even zero cost proxies, we always evaluate them in a vacuum, and there's little to no applications after that. So we don't really know actually what happens on real world problems.
Okay, but I mean, in chapter 1, I forget about the manuscript. I'm sorry about that, but I already read it since. I saw that you have an application with EEG signals, right? It was with few shot NAS or not? This one.
So in our EEG application, we only defined the search spaces. We did not have time. So first of all, we did not have time to apply a pipeline.
Okay.
Yes, and also in our case, we were working with the transformer search space, and so no, either we were working with the 1D convolutional search space, and then because EEG actually the amounts of data are quite small, the training times are very small. So it is possible to work without methods that try to reduce the search time. So we did not try. And then when we went to the transformer search space, we considered that probably this would be useful, but also we were more focused on establishing this MAE framework that basically has never been done in NAS.
Right. Good. Yes, I moved to the zero cost proxies that you mentioned in the last section. So often we have a weak correlation, as I said earlier, with the true performance. And many of these do not consistently, let's say, correlate with the actual final accuracy. And you mentioned that in the manuscript, and this is true. And also another thing that is like probably very important, that a simple architecture measurement, like the number of parameters, may reveal actually or often outperform these sophisticated, let's say, proxies. Why? I'm just trying to understand in the ranking network. So what this means? Yes.
So very good question. In the benchmarks, we do see that parameter count outperforms a lot of metrics, and yeah, we don't really know the explanation. That's one of the things that the literature is trying to explore. One thing is for sure is that many of these metrics do use some data. So there's always the inherent instability of using a specific data point, since it's always like one forward pass of the network to compute, then you're actually quite reliant on the data point that was used. And this could explain some instability, but of course, yeah. I think the fact that there is a forward pass in the first place and that the network is freshly initialized means there's just a lot of stochasticity involved in these metrics.
Right. Okay. Do I have time, Mr. the President?
Yes.
Okay.
Yes,
so I have probably a couple of questions more. So do you think that there is kind of interpretability of these proxies, or could we have this kind of interpretabilities, or it's impossible theoretically, to?
So the metrics themselves.
Yeah, the fact that, okay, I understand that there is a lot of intuition behind these things. So to see the gradient with respect to the Fisher proxies, and so on. But is there any, let's say, because this is a critic, I mean, that we can put everywhere with these the measurement, we need to interpret them. Why it correlates well or not with the performance? Is there anything that you can mention here?
So of course, the metrics themselves, they are always constructed based on some other part of the literature. So I mentioned, I think in the manuscripts, that all of this is very adjacent to information theory. And basically all of the metrics come from information theory in some way or another. So of course, there should be intuitively something behind all this, but it's not really backed up by the results.
Yeah, here in many works that we are doing also, we are doing, let's say, pruning, for instance, the pruning. We visited the pruning. The pruning is also derived by this kind of metrics. And we keep only, let's say, the weights with high gradient, with weights with probably high value of any proxy. And yeah, it worked. But of course, the fine-tuning part, when you retrain the model, is very important also. Even if you do a random, let's say, pruning or random proxy, kind of. And why, I mean, the literature review are focusing on these kind of things? I'm asking myself, not both. So it's kind of yes. If you can add, yeah, thanks. So to see these limits in terms of results and make probably methodological choices that probably gives better performance at the end. Do you have an idea?
Yeah, so as you mentioned, this is all based. This tends to all be based on the results. Even actually, when we look at what kinds of papers in this field are published, it's always the ones that have the highest correlation or something. Even if the theoretical insight besides it is actually quite minimal. So, for instance, there's this swap metric here. What's really interesting about this metric is that if you read the paper, you realize that they just reframed another metric from another paper. So there's like basically almost no novelty, but they just have the best correlation, so they end up being published. And that's also something we looked at so we did try designing also ourselves some praxis during this thesis. And the reason that they are not here is because it didn't work, obviously. We did not get good correlations, although we thought that probably the theoretical insights that we used were quite interesting. And there were some really good interpretations of this. So I'm thinking, for instance, about this idea of the Lie derivative, where it was very geometrically oriented consideration of the models. And it ended up not giving anything in the benchmark, so we never published it. And yeah, it's a very results-driven field.
Right. So last question. I swear. Yes, the Spearman rank correlation that you mentioned it at the end, and you change that. And this is basically, you are saying, because it's at the let's say when you reach the performance, high rank, top rank, right? Architecture. Could you just give me more details on that? Why it's not working? Why it's not working? In your point of view, I mean.
So I believe the bias comes from how these metrics were benchmarked in the first place. So if we look at Spearman rank correlation and we see, for instance, very high number like 0.8 here, we can say, oh, this method performs great. It really correlates well with the actual training of a model. And when we look at what Spearman correlation does, it's only really separating the bad architectures from the good ones that matters in this case, because in the search spaces, at least in the tabular benchmark, in the benchmarks that we use, most of the search space is very bad architectures, and there's a very little number of very good architectures. And so basically having high correlation on these search spaces means that you just remove the bad architectures. And that's why looking at the top 1% was so important, or like top K%, but we chose this specific value to just say that these metrics do not perform so well when we are looking at what actually matters, which is the good architectures. And in my point of view, I think the fact that we have been using Spearman rank correlation for so long for these benchmarks also has dictated what kind of metrics are created. And basically, maybe using some other metric to benchmark this would mean that we find other types of metrics. And that was the primary aim.
Okay, thank you very much, Timotée, for the answer. The presentation again was very good, very interesting. Probably I didn't see the number of the slide number, so it was very hard to check. But yeah, this is just a remark. And yes, I would like also to thank the supervisors for the invitation to review your thesis. And I give the floor back to the president. Thank you.
Okay, thank you, Professor Tabia. Now I give the floor to Professor Nicolas Gac from University of Paris-Saclay.
Thank you, Mr. President. I really appreciate your work on the. What I appreciate most is the reflection you have on the state of the art. It's difficult to have a zero-cost proxy on all the paper of the NAS and to know which one is the best. Like you say, the swap, you're not really convinced about how they done their work. And I think that the best of your work is to have some compasses, to have some guideline to understand this challenging topic, the NAS. Because there is so much space to explore. There is not, as you presented, it's not only one problem. There is lots of sub-problem inside. And I like when you choose some ID to have a look on the rank, for instance, to choose, for instance, for the split, to keep the idea of the gradient matching, because there is in that topic, I'm not I have supervised only one work of a student about NAS, so I don't do day by day work on NAS as you done. And I like the idea to find not to replace a heuristic way to do NAS with more and more optimization tools. So first, I have a question about chapter 3, because as a reader, has a little frustration to not to see the NAS method applied to it. But I think that you are the first one to be frustrated not to apply it on this data. What, if you have time, would it be possible? What it means to do it, to apply your method on the EEG data?
Right. So the structure of this chapter about EEG is, I think, yeah, quite, as you said, it quite frustrating to read, because we have first this very simple search space that we devised, which is this one, which is based on some 1D convolutions. And basically, when we started working on this, and like several months later, my coworker Yassine came up with some new idea to instead do a foundation model on EEG data, and that's what led us to just dropping this idea. Basically, like just the speed of the field, where we go from 1D convolutions, and that was the state of the art at the time, and straight to foundation models. So of course we didn't really do anything for this, and then we moved to this more ambitious transformer subspace idea. So my guess is that if we wanted to apply some NAS methods to this kind of framework, we would probably reuse some ideas from the few works that have worked on transformer before in the NAS literature. So for instance, there's Autoformer or some more recent, I think some more recent work did actually look at masked autoencoders like in this framework. So yeah, actually this, in the context of EG data, also with the fact that the training times are so low, I think we probably could get by with some pretty standard pipeline with just like, for instance, Autoformer and train from scratch or something. At least that's how I envisioned how I would train this.
But you can have your tabulated benchmark. In fact,
I don't think I could create a tabulated benchmark, but yeah, there's none for transformers at the time.
But for the convolution one,
for the convolution one, I did mention, yeah, that this could serve as a tabulated benchmark. It would be a challenging search space. Also, because this is quite important, because I think all of the tabulated benchmarks so far have been about image data, and yeah, that would be a new data paradigm.
That could be a contribution to provide.
It could be.
Yeah. I have a question on the slide 46. Just to help me to understand one figure that, yeah, in fact, the sub figure at the corner right at the bottom, you didn't comment, in fact, this in the manuscript in here. Can you comment how you split the graph?
So basically, once we have a similarity matrix, it's an optimization problem called a main cut optimization, where we just make the cut. We spread our metrics on some kind of 1D axis, and we make the cut such that on each side the metrics are the most packed together.
But here there is two axes. Why?
No, it's just like the representation of the cut. It's not an axis. Yeah.
Okay. And about the SuperNet, about the few shot method, could it be a sequential, like to focus only on certain to do the SuperNet split on only one link, and then to focus on that one, and to divide the exploration. You have a first step. You create all the SuperNet.
Yes.
You train them, and then you do the exploration.
Yes, exactly.
Could it be more divided, like a sequential way? We construct the first level, a hierarchical way. We construct the first level of the SuperNet, and then we, as you do ablation, in fact, you select only one. You do your NAS exploration, maybe not so all exploration, and then you split afterwards.
Yes, actually, that's very interesting. It would be kind of like doing some kind of Monte Carlo tree search, but on our splitting tree. And I think that's actually a quite interesting idea, because we could just like start searching one branch, then backtrack when the performance is found to be not that good, maybe based on some preliminary results, or like low fidelity estimation on that SuperNet, and then we can just backtrack. But the one problem I see with this is that probably it would still be more costly than creating all the supernets and then selecting one, for instance, based on the criteria I showed before, like the validation accuracy, which we showed that it's flawed, but it would probably still be more efficient than this kind of search.
Because the training of the level high, quite high on the first level.
Yeah. Basically, we would add all the trainings of the intermediate levels.
I've got a question on the Paradis. So first, to understand, is it on the manuscript you speak about a setup for the genetic algorithm? It was page 44, but you will understand about these 4 setup.
Yep.
And for Paradis is setup 4. Because I think you didn't mention.
So yeah, I have a slide about that. So I mentioned the 4 setups that we. So it was basically some kind of ablation on what kind of genetic setup works best, which to our knowledge had not been done in the literature yet. And our 4 setups were the following. We just have the regular evolution where we don't use tournaments. Then we use the one with tournaments. This one is like tournaments, but we only use the results of the tournaments for the exploration, for the mutation and crossover parts. And then the last one, we try to use multiple tournaments. And what we found, basically, we used in the end this one, the C in the method, because what we found was that actually there was no significant improvement from this one to this one, but the A and B they tended to collapse to like a single to like one very same population at every each time we run it, even on different seeds.
Because in the algorithm 3 in your manuscript in page 81, you have candidate A from P random architecture and candidate B from all the remaining architecture in population. So I see it. Maybe it's not.
Maybe I don't know. Maybe I forgot to update the algorithm, but I think I think that's not the same as setup C.
Okay.
But yeah, maybe that's an oversight on my part.
I would say that if I understand well the algorithm 3, you take one. You pick the best in A. If we have a look on the C figure, you pick the best in A, then the best in B, the rest of the population, the remaining architecture. And so you do mutate on this best one and crossover.
Yeah, so that is probably an oversight on my part. One of these 2 is true, but I can't.
It will be a E setup. In fact,
yeah, maybe.
And what I understood of your what I understand of your Paradis algorithm, the idea is to pick up if you have the Gaussian elsewhere figure. So in fact you eject the architecture with the outlier.
Yes, we remove the ones that are on the tail of the distribution.
And it's a parameter. The one who have too much parameter or the one who have.
Yes, at that time of the schedule. And basically what this does is that at the start, since we start with a positive schedule, then the small architectures will be removed first in the training, and then towards the end, with negative temperature, then we kind of have end up with the middle point of architectures. And this is based on some observation actually that the top ranking architectures tend to be not the biggest, but something a little under that.
And you could apply this method of Gaussian, reject the outlier for other metrics than the parameter number.
Yes, we could totally.
Okay. And so your idea of Paradis is to decorate the exploration and the ejection, the metrics.
Yes, they are based on different metrics, but we also believe that most of the metrics tend to have some kind of bias on parameter counts to begin with. Actually, that's been proven for some of them in entire work. So it's not like completely decorrelated because parameter counts is kind of a part of the other metrics as well. Like at least we can't prove a decorrelation.
But what I don't understand in the standard method, how they eject the.
They remove the architectures with the low scores of ZCP.
Okay. I've got a question now about hardware aware. I work more on architecture implementation. I agree that it's NAS is really can help a lot in that topic. And in all your work, how you can have your idea to integrate this hardware in the split? Maybe is it possible to integrate hardware metrics during the split? Or
Yes. So hardware measurements I believe, can be used as any other metrics. Actually, most of the time in NAS algorithms, they are used in the objective portion. But we could also consider them to be some zero-cost measurements that can be used like in every other context that zero-cost proxies have been used. So for the splits, as ad hoc zero-cost methods also.
the ejection here, you could
Yes, we could
weight or
and
weight
yeah.
heavy weight for the architecture will be too costly for hardware.
Yes, or for instance, if we are constrained by latency, then can also use that. So yeah, I think this is also why NAS is so interesting for hardware related tasks, is that it's very flexible in what can be achieved using also these hardware measurements.
And if you had 1 year more of thesis, which architecture you would choose to test this kind of idea? GPU, FPGA, little CPU. In which direction you will go?
So I think for practical reasons, I would probably use GPUs. But I know that actually I'm also very interested in applications for FPGA, so related uses. But yeah, at least to prototype the methods, I think GPUs are safer.
And the last question.
Yes.
So the NAS is a new domain, a new community. How could be to help this community to progress? Yeah, all together. What is missing as tool for open tools? There is already the test bench the NAS bench 201. What kind of tool you would be if you have your own objective to contribute to the community? Which tool you will help to propose?
So I think in terms of the algorithms, for instance, they now, as I said, they tend to be very packaged in very convenient means. So for instance, I think Meta recently released their own HPO/NAS tool. So I think at least as an academic researcher, probably that's not the best idea to try and go in that direction. I think where we are the most lacking is still the search spaces. So even though there's already benchmarks, I think just coming up with ideas to be able to use the more expressive search spaces more consistently would be a great direction.
To what? To search space more?
Yeah, to exploit the more expressive search spaces. So for instance, Einspace is very expressive, but also it's so large that you can't benchmark it. So we need some kind of tooling to be able to know what to push the literature in a direction that they may want to benchmark on. This kind of stuff also.
Okay, thank you.
Okay, thank you, Nicolas. So now we move to the third member of the jury. I give the floor to my colleague, Assistant Professor Jovita Lukasik from University of Siegen in Germany.
Thank
You
you,
have the floor.
Mr. President. First of all, thank you very much for this presentation and for the talk. It was really good. And I'm every time very happy to see people still working on NAS and zero-cross proxies. So that's great. So I would like to start with some more detailed questions about part of your presentation. If you could go to slide 43, please. Yes, exactly. So just like to be clear, you first of all train your super network and then you do the splitting, or do you do the splitting while training the super network, or where do you get the gradient matching from?
So I think in the original work they did train the network beforehand, and then in between each split they applied like a few warm-up epochs. And in my own framework, I think I bypassed the warm-up, but there's still like a SuperNet training at the start.
Okay. So first you train the super network and then you
Yep.
do the gradient. Okay, and then about the split distance itself on slide 48, how does it differ to the edit distance in a graph? So you know about the edit distance? What did
I don't recall.
Oh, no problem. So it's actually just like the difference of how many steps do you need to do to go from one graph to the other. So how many nodes do you need to change in base of operations? So how many edges do you need to change?
So I think it is quite similar, except we are isolating only like only one edge of actually. Yeah, I'm not sure. It's been so long since I designed this. Actually, I created this when I was like in internship, so like 4 years ago. And I maybe I did not check, and it's the same thing as the edit distance. But I think it was. I think when I checked, it was not that, and it's specifically for groupings for like groups of.
Perhaps more.
Yeah, it's like in the case where you have several superimposed edges.
Where you want to compare two sets with each other and not just like two graphs. Yeah, that makes sense. Otherwise, I would have suggested to look at several edit distance algorithms, because I'm pretty sure they are very cheap and easy to count and calculate nowadays. All right, that makes sense. On slide 50. Exactly. So you compared your few shot approaches against different kind of no splitting and different kind of zero cross proxies. So which works very good in general are probably pruning based approaches. Yeah, SNP is I think a pruning based zero cross proxy, as I
So the pruning based or SNP grasp and SynFlow, as I recall.
Exactly. So have you any intuition of how, for example, TNAS would work on few shot NAS? which also is kind of a pruning-based zero-cost proxy approach.
So TNAS is like the concatenation of NTK and yeah, okay.
Exactly.
I remember. So the algorithm of TNAS, you mean where we just remove the edges one by one.
Exactly.
So I think it could also work, but we just have to like ignore or like. Yeah, I guess it can still just work out of the box, and we just ignore the fact that there's less edge, less operations on one edge or several edges.
Yeah, because I mean, eventually you could just like use both approaches jointly and maybe have some even more improvements on that. Because they used to do zero-cost proxies already in conjunction with each other, pruning based, and I guess if you want to really do some splits in your few shorter.
Yes, because when we think about it, TNAS is basically just like progressive search-based shrinking. So it's kind of the same.
Exactly. Okay. And then in general, maybe one question. So you're talking a lot about Spearman correlation. However, I'm wondering why explicitly Spearman correlation, not Kendall-Tau.
That is also true. So I just think it's based on the fact that Kendall-Tau has not been used so much recently in the benchmarks. So I did actually, I think originally there were a lot of works that used Kendall-Tau, especially the ones that evidenced coadaptation and weight-sharing issues and stuff. But yeah, I'm not sure exactly why, but the literature seems to have moved on some from Kendall-Tau. And it's true that in the strictly mathematical sense, if we look at ranks, then Kendall-Tau would be quite useful.
Given the definition behind Kendall-Tau saying I want to properly rank two objects with each other, because Kendall-Tau is just like checking how correctly do I rank objects with each other. So therefore, I don't know the NAS bench suit 0 how it looks on Kendall-Tau. I know that we looked at that once, but a long time ago. That would be interesting to see if you would have different results coming from that.
So I'm thinking that probably the Kendall-Tau, because it's just the sum of whether the rank at this whether the two rankings at this exact rank are in agreement. I think actually I preferred the idea that is here. So unfortunately, I do not have a slide for this formula of the agreement. But basically, it just looks at whether all of the number of architectures in one ranking that also in the other rankings up to depth D. And I think that is like likely even a little more suited, a little better suited to this than Kendall-Tau.
That makes sense. Yeah, agreed. Okay, thank you very much. Now maybe some more hypothetical questions. So there are two parts, I think, of people in NAS who would agree with your first statement of saying NAS is a part of HPO. I guess it started with having that opinion, and after your PhD, are you still thinking that NAS is part of an HPO problem, or do you think it's like two sub-communities where both of each other benefit from each other?
So, like, personally, from like the purely mathematical standpoint, for me, these are basically the same problem. Just like you change the set of hyperparameters and you say, oh, in the case of NAS, the search spaces are a little more complex. And yeah, it's basically just HPO but harder. Or like maybe, or just like a hard, more like the part of HPO that is hard. That's more like how I would say this. But it's true that in terms of communities, it's very different now. I think probably the two communities were more interlinked when Bayesian, like bio read stuff was the standard. But now that we move on to stuff like one-shotness and zero-cost proxies, yeah, those are things that we never see in HPO.
That's why I came up with the question, because like zero-cost proxies and few-shot or one-shotness, I don't see that in HPO.
No, I mean,
Therefore, and in general, zero-cost proxies. So you looked a lot into how good are zero-cost proxies and benchmarked them, which was great, especially like looking at the top one thing where zero-cost proxies are just like really not good at. So they are like you also said, they're weak regression, or maybe he was that the weak regressors actually being good at discarding very low performing architectures. So would you think that using several of those zero-cost proxies in conjunction would help your methods? So not looking only at one zero-cost proxy, but looking at several, since they are, depending on what kind of task you have, what search space you have, they perform differently.
First of all, it's been like actually proven that they perform better when we sum a lot of them, or like even this work by Katlekova et al. And that you were also part of, that just use them as features for AdaBoost. But the other thing is that, so I once had the reflection that actually there's two groups of zero-cost proxies. Ones that are like you just that actually need some data, and for instance the pruning ones, and the others are like just properties of the model that we don't like. There's no theory behind it. It's just like properties. And I think actually that it's quite likely that the first group tends to just predict the first ones, the second ones. They tend to be predictors for other properties of the model, or a group of properties of the model. And in this regard, like just ensembling many of them, probably it would be too much, because they are all related in some way. Especially if we also add some just properties in the mix.
What do you think are like biggest disadvantages of actually using zero-cost proxies or relying completely on zero-cost proxies?
I think, if I'm being honest, I don't think it should be. I don't think it should be a point in zero-cost proxy papers to say that we are trying to find good architectures. What we should actually focus on is the fact that they enable quick exploration of entire search spaces. And I think this whole trying to benchmark performance of zero-cost proxies thing on darts, like it does not really add up, because that's not the goal of these methods.
Okay, I have two last questions. So at the very beginning, you said it's very hard to discover new architectures, or also focusing now that you want to focus on Einspace, for example, or would focus on Einspace if you would have a year more of a PhD. So do you think NAS, as it started with focusing on cell-based search spaces, now probably focusing on CNNs, now going more into transformers? Is it maybe the issue of us humans being too biased to only work on things we know which work well? So transformers going to vision from language, CNNs based on how we approach, or like cell-based search space, how we approach CNNs with ResNets. So do you think it's actually our fault that NAS is kind of stuck somehow?
It's difficult to answer because, of course, when NAS started out, the hype surrounding it was always like, we are gonna find the next big architecture, right? And as things evolved, just became, oh, we're gonna find yeah, I think it's the problem is mostly just how the fields needed some way to benchmark itself. Otherwise, otherwise you could point at some logical fallacies, and then this kind of was blown out of proportion to to a degree where we forget what's the initial point of it. Plus the fact that it kind of got overwhelmed also with the explosion of the training costs and on the fact that the entire deep learning state of the art is now large models. So NAS can't really benchmark itself on that.
And now, if you would start your PhD from scratch, day to day, with foundation models, what would you do? Yes, of course. What would be kind of a first step where you would say, yeah, that is something interesting, important?
I think the easy answer is compression. It's like just deriving models from the base ones to be able to deploy them on more diverse contexts. I think that's actually, I believe that's just the starting point that any thesis should go on with NAS nowadays.
Thank you.
Thank you very much. So now my turn to ask questions. So what is interesting to be the last one, I mean, before the supervisor, is that the most interesting questions have been asked, have been given. So this is one thing which is interesting. So in my opinion, I mean, in NAS, as you mentioned, Timothy, you have three components. You have the search space, you have the search algorithm, and you have the evaluation is done, right? Three components, okay? How to define the search space, how to explore the search space, and when you pick one architecture, you have to evaluate it. Okay. So, in my opinion, also your two most important contributions were in how to evaluate by evaluating. I mean the evaluation of the accuracy, not the rest. I mean no time, no energy consumption, only the accuracy. And in this perspective, you propose this zero cost proxy, if I am not wrong, with different variation, with different, let's say, implementation and so on.
So this is, yeah, the field that one of the fields that was studied.
Okay. Okay.
So yeah.
So in this point, I mean, for the evaluation, the zero cost proxy, I have two questions. The first one is the overhead. I mean, if you compare the splitting and with no splitting, okay, in my opinion, probably you can say, yes, I agree or I don't agree. You have cost, you have additional cost, you have an overhead. I mean, when you do splitting, probably, this is what I want to check with you. What is the cost? I mean, did you try to measure in terms of execution time? Because you know that, I mean, when you do training is one of the biggest and the most expensive phase in the design of architectures. And probably when you are splitting, this could even make the training even more expensive. So, I mean, did you try to measure? I mean, if you do splitting and no splitting, how much the overhead will be?
So I never measured it properly, but I actually it just depends whether you try to retrain the supernets in the middle. If we don't, then the search is done in 5 minutes. The splitting is done in like 5 minutes.
Okay.
And if we do, then it could take a little bit of time. It just takes, like, it scales with the time of the training. For instance, if we warm up for one epoch, then it just takes one more epoch for each subsequent.
Okay. So, I mean, in terms of overhead, I mean, the conclusion is that the overhead is negligible. I mean, it's something which is not
negligible,
too much.
Negligible compared to fully retraining the architectures. Yeah.
Okay. Okay. So this is the first question about the evaluation, about the training. So what is missing in general in my point of view, Timothy, is that, I mean, at the end you present techniques. I'm sure these techniques are very interesting, but what is missing is values. So at the end of the presentation of the technique, as the reader, as people who are listening to your presentation, I was looking for values like to represent the general benefit. So you presented, for instance, different kind of tables, different kind of like this correlation. But what was I mean, can you please explain, for instance, if you take the correlation, the Spearman correlation, with your adaptation, with your how to say techniques, with your implementation and contribution, what is the benefit at the end of the story? Well, how we can measure the benefit in terms of speed, in terms of gain? I mean, if you can take, for instance, one table, you
Yes.
Can just share the screen again.
yes. For instance, slide number 59, for instance. Yes, this one,
Yes.
58. So here you have the ranking with the Spearman, right? And you propose something which is, as you mentioned, I think the presentation and the how to say the weakness you presented is very interesting. Spearman ranking is very interesting, but the weakness is that Spearman is not able to select or to rank among the best, the group of the best architectures. So okay, so you present something, you try to cover this weakness, and what is the gain? I mean, how can we measure the gain by your technique in general? I mean, in overall, what? Okay, so let's suppose I am consumer, I am your client. You can say, okay, with my technique, I can assume we can guarantee that you are going to gain this kind of percentage, for instance.
So first of all, it's quite hard to define a gain in terms of, for instance, the Spearman benchmark itself. And yeah, the reason, for instance, when I presented these results, there's a reason that we used the raw rank is that the method in the end always tries to find the best architecture that it can find.
Okay.
And that is quite different from ranking all of the architectures that it sampled. So I believe with the way we did it by displaying the rank of the best found architecture, that could be a quantification. For instance, just like the difference of the rank that we have could be that could be a quantification of the gain.
Okay, I think this could be very interesting. I mean, probably in the future, if you have the possibility to extend or to make some measurement or make some experiments, this could help your publications, I mean, to have a higher impact, in my opinion. And the same for the search algorithm. So you presented a new technique for the genetic algorithm, right? You propose a new adaptation, a new mechanism to do genetic algorithm. But what is missing also the same. So we didn't see a value that demonstrate how are we better than the naive implementation of the genetic algorithm? Can you please, I mean, explain? So with my genetic algorithm, I can guarantee that we have this value of speed up, for instance, in the search mechanism, in the exploration. You see my question, Timotée?
Yes, yeah, that's definitely something that we did not take into account in this paper, at least. Especially because, once again, it's quite hard to compare when, for instance, the genetic algorithm itself may select different architectures that are sampled. So we can quantify the speed up to, we would need to quantify, for instance, the speed up to reach some specific accuracy. I think that would be the best way to quantify this.
Okay. Finally, my last question is for paradise and multi-objective exploration. So in the talk, in the presentation we did, you apply paradise for only one objective, which is accuracy.
Yep.
I mean, if we want to apply paradise for multi-objective exploration, including execution time, energy, and so on, how are you going to proceed?
I believe it's actually quite straightforward. Since these hardware measurements are they do not require any training, only like on device measurement, then we can just replace the proxies with the measurements.
Okay. But in this case, we will have multiple metrics. So how are we going to choose the best architecture among all this Pareto frontier?
I guess there's different approaches to this. simply summing them in some way and making them one objective could work. And if we are trying to explore a Pareto front, then we could have some weighted sum and then make the weights vary such that we target a different pocket of the space.
Okay, thank you. Last question. Sure. Okay. So is there the possibility to adapt the search space to the search algorithm? So the idea is simple. I would like to have your opinion. Is it possible, for instance, to extract during the exploration, to extract some knowledge, some hints from the search, from the search process to choose or to adapt the search space? I mean, to either to increase, to expand the search space, to include new operators, or at the opposite, to shrink the search space just to focus on some very interesting and some efficient architectures. Is this possible with your methodology?
So with my methodology, I don't know, but in general, I think this is possible with any NAS algorithm. The fact, for instance, if we find that the algorithm goes into specific directions of the space, and for instance, like a concrete example would be if we find that our search algorithm consistently goes to the deeper architectures, then that might inform, for instance, that actually probably if we go even deeper, that could be a good direction to modify the search space. So I think, yeah, the search can inform also the construction of the search space.
Okay, thank you, Timotée. Now I give the floor to the supervisors. I will start by Abdeljalil. Professor Abdeljalil, if you want to ask a question or comment or what you want.
Thank you very much. I just have general comments, but I will move in French if you agree, Mr. President. Alors, Timothée, tout d'abord, je vais remercier les membres du jury d'avoir accepté et d'être présents, certains en direct et en visio, cette soutenance de thèse. Merci aux rapporteurs pour leur rapport et merci à Novita et Monsieur le Président de votre participation aujourd'hui à ce jury. Alors Timothée, je tiens à te remercier pour cette présentation. Moi, je ne vais pas poser de questions, bien évidemment. Donc, je vais te donner quelques remarques et plutôt, c'est des commentaires généraux. Tout d'abord, comme je disais, merci pour cette présentation très pédagogique à mon sens, que j'ai trouvé très claire, très progressive dans le sens où ça a permis de bien positionner ton état de l'art, qui n'était pas si évident à mettre en évidence, afin que tu puisses mettre en perspective tes contributions à travers l'état de l'art. C'est vrai que c'est un domaine assez particulier, assez pointu. Donc bon, je pense que tu as réussi, à mon sens, à bien présenter la chose. Donc, écoute, globalement, le déroulement de la thèse s'est bien passé durant ces 3 années, quelques mois, on va dire. Bon, je pense qu'on t'a vu progresser. On se connaît depuis que tu es élève ingénieur ici à l'IMT Atlantique, sur les UE de la FMCE. Et on a vu la progression et moi, ça me fait plaisir personnellement de te voir ici avec l'évolution que tu as eue durant ces quelques années. Tu as gagné en maturité et ça se reflète un peu sur ton travail. Et globalement, ce qui était appréciable dans ton travail, c'est que tu baissais pas trop les bras, tu étais assez pugnace, ce qui est une qualité en recherche, malgré des fois, comme tout le monde, on le sait, en recherche, tous les résultats qu'on a présentés là impliquent qu'on a eu des échecs, je mets des guillemets entre échecs, sur des choses qu'on n'a pas réussi à aller jusqu'au bout, développer ou des résultats non pertinents. Mais voilà, ce qui montre un petit peu ta ténacité, dans le bon sens du terme. Et comme je dis globalement, la réussite d'une thèse, c'est un triptyque, c'est le sujet, l'étudiant et l'équipe encadrante. Et je souhaite remercier Mathieu pour son implication. Il suivait de plus près que moi, bien évidemment, l'encadrement de Timotée. Et écoute, je te remercie aussi pour ta contribution dans la thèse. Voilà, je vais m'arrêter là.
Merci beaucoup.
C'est vrai.
Je vais donner la parole à Mathieu.
Okay, thank you, students. So I'll do it in English.
Okay. You're welcome.
So yeah, first I'd like also to thank Nicola and Hedy for their review of the manuscripts and yeah, thorough review of the manuscripts. Thanks to Smile to have served as the president and to Yovita to come to the far, far west. So thanks a lot for your leadership. Yeah, thank you, Jalila, for your confidence on this thesis and your support, and very happy to have worked with you, both of you, and I learned a lot from this thesis. That's why we do this the first hand. So yeah, I'm glad to have done it. I wanted to say that we set the bar quite high in terms of expectation at the beginning of the thesis, and the objective was to contribute actively to the very field of NAS and not trying to go on sideways. And I think that through your contributions, well, you have contributed to the discussions around NAS, and we always had like good feedback from the community when we went to AutoML and other stuff. So for me, the contract is really filled. As Javis said, in every PhD thesis, there are some bumps on the road, and there are also walls on the road. And as Javis said, you showed a lot of resilience and perseverance. And yeah, I wanted also to say that. I wanted also to say that you did not do any compromise on the results that you have shown in your papers, and that when you had things to say on the problems of the NAS benchmarks or on the weakness of zero cost proxies, then you show it, and you didn't try to hide anything. And I think it's very important for the field also. That's it. I think these are both qualities for a good researcher, and I hope you will continue on this path. And I thank you a lot for your work over these 3 years. And that's
Thank you much, Johan. Donc, merci Timotée pour la présentation. Thank you for the presentation. Now we will move to the deliberation. For this reason, we are going to stay here, and I will invite the assistants to come back later. On va délibérer ici. On va revenir ici vers dans quelques minutes.
On se fait des locaux pour mettre les invités dans une salle libre. Vous installez ou le centre libre. On viendra vous chercher. Merci.